I'll be giving my presentation on GNSS space clock assessment using IGS and MJAX products on behalf of my two colleagues, which unfortunately they cannot be here. Anyway, to introduce a little bit, we at INRIM we are involved in characterization of atomic clocks and timescales in GNSS for about 15 years now, and through different projects with our partners like the ESA, GSA, and Thales Alenia Space. We regularly do analysis of space clocks in terms of time offset after the second drift removal, the normalized frequency offset, the frequency stability via Allen deviation, and the frequency drifts. And we do this for constellations like GPS, Galileo, of course, Beidou, and also GLONASS. We base our analysis on public data we take from the IGS, and for some years now we've been taking the MJAX as well. In particular, we are involved in a H2020 project called DEMETRA, and we exploit time services. There are 9 of them, and one of them is called time integrity, in which we monitor the status of Galileo satellite clocks, and we detect the possible anomalies, and we can generate alerts automatically. For example, it can be shown here that we have anomalies detectors like the frequency jump detector, which can be seen with, as a red bar on the graph, or the frequency jump detector, or even the drift changes detector. We make analysis of the stabilities of the clocks, of the constellation, via Allen deviation, and then if any anomalies detected, we write them in text files, and they can be sent to users in case that to warn the users that these anomalies happen, and they should not be used in the computations of their applications. We really like to investigate the quality of these data, because it's also just our project is also an experimentation. We start from GPS clock data available from the IGS, because it's been going on for a while now. This is nothing new. It's from the IGS website, the product availability. We noticed that the final and we noticed that the IGS has been working very hard to reduce the latency of their analysis from the final, from days to hours of the rapid, and then we noticed the ultra rapid, and then we focus on that because we also want to reduce the latency of our analysis and moving toward real time as soon as possible. So I'm going to show you some results comparing the final, the rapid, and the ultra rapid clock products of IGS, if it works. Okay, here we go. It's just a bit slow. On the left, it is the phase offset of a GPS satellite after the second order drift removed. The blue curve is the data taken from the ultra rapid product. Red is the rapid, and the green is the final one. And we can see that there's a good agreement between the final and the rapid results. On the ultra rapid, you can see a bit of difference, but the trend remains the same. And we try to understand that by looking at the frequency data, and it is quite obvious that the rapid and then the final agree, but there are outliers, large ones that can be seen on the ultra rapid with respect to the other two. And they are of 6 hours. They seem to be regular, so that could be associated to the discontinuity of the data of the ultra rapid. All in all, on the phase, it is of about peak to peak about 3.5 nanoseconds with respect to the time scales of each product. So it can be seen that the clock on the satellite is being managed quite well, and it can also the stability of the clock can also be seen with the Allen deviation. But on another satellite, of course, anomalies happen sometimes. We see a frequency jump from the frequency data, and it is of about 1 times 10 to the power minus 12 relative units, and it can be seen on all of the products. And so from this we can conclude that it is possible to use the IGS data to detect these anomalies, although it is necessary to properly manage the outliers on the ultra rapid. Concerning the MJAX, we collect data from MJAX, in particular these 4 analysis centers, because not all of them produce all the constellations and also report the station clock data. The sampling interval is and the clock and the product, either the clock or the orbital files are taken from the MJAX website, but the latency we have to conclude it ourselves because it's not available. Sometimes they change. This is just some average value. We do appreciate the fact that MJAX try very hard to produce the data and make it available to us. And although and this data is concluded last year, and we are really looking forward to looking at the latency again to see the improvement of the project. A similar analysis is done on the on a Galileo satellite. And of course, the phase offset after the second order drift removed, we have the blue curve, which is not because of the range, so it's not so very well visible, but it's from COM. We have the red from GBM, the orange yellow one is from GRM, and the last one is from WUM. We see that then they don't really have a common ground in this. They have some discrepancies. And it can be seen very well that there is a day boundary jump that is very easily seen, can be seen easily on the WUM products, show also as outliers on the frequency. It's quite particular to look at the stability using the island deviation, because of course as there are jumps, the stability of this satellite, as seen by WUM or as processed by WUM, is a little bit lower than the other ones. And there's a funny bump of the curve on GBM products, and we don't fully understand why, even though that say they have less day boundary jumps, but probably the sinusoidal effect that is very visible on the phase data can be one that can contribute to this stability problem. Although, of course, we're here, and I would like to, if anyone can explain these phenomena to me, that would be really nice. And in another, if we have this kind of day boundary jumps, it really does affect the analysis, because if you can't really have a continuity of your data. And so we noticed that we were in contact with MJAX some years ago, and we learned that the analysis centers have their freedom of choice in analysis algorithms or reference clock that can change day to day or as they want, and we cannot explain that. So we decide to align the clock data. We align, and you can see that the day boundary jump of the WUM product can be of 15 nanoseconds. That's quite large. But after aligning to a common reference throughout the analysis period, the stability increased, and the day boundary jumps have been largely diminished. So that should help us with understanding the true behavior of the clock on board the satellite. And so to conclude, it is possible to use the MJAX and the IGS clock products to assess the onboard satellite clocks. but we have to have pre-processing algorithms to detect the outliers, to remove them, to align them, etc. And we hope that our analysis is really useful for GNSS users in general, and also for space clock manufacturers to understand more the behavior of after launching, and for scientists, of course, those who are interested in understanding the clock non-stationarities and performance. Thank you.